we'll be solving some calculation question on the electric potential we just taught. The theory aspect is already online already, but I'll be doing the calculation aspect. So they said 2-point charge Q1 equal minus 2 microcoulomb located at x naught. So let's assume this is where Q1 is at x equals 0, and Q1 is equal to minus 2 microcoulomb. Then for Q2 is equal to plus 2 microcoulomb located at x equals 50 centimeter. So if I have to convert this value to meter, it will give us 0.5 meter. So give us 0.5 meter. Then located at s equals to 50. They said the work done by the external force to bring a charge Q3 from infinite to s equal to 100. So another charge Q3 of 1.5 microcoulomb was brought closer at s equal to 100 cm, which is equal to 1 meter. So we're told to find the work done. So from the diagram here, you find out that this is a negative charge, this is a positive charge, this is a positive charge, since there's no sign given there. We're told that this charge was brought from infinite, from a far distance. It was brought close to this point. You'll notice that this Q1 and this charge will experience an attraction force. Right, this one and this one, they will experience a repulsion force. So in order for us to calculate the external force that was exerted on Q3, the external force that was exerted on Q3 by these two forces, we'll be using our superposition theory. Solution. So we are looking for the value for U, the work done, and our U is equal to summation K Q naught BQ all over R. Let's give this one I, let's give this one J. So if I were to apply this formula to this stuff, our reference charge, or rather the test charge here, will be the Q3, because it was the one that was brought from infinity. So to now be equal to K, the reference charge, our K number is 9 times 10 raised to the power 9 Newton meter cube per coulomb square, times the Q, that is our 1.5, times 10 raised to the power minus 6. Then we'll be multiplying it by our charge and the distance between the charge, and our charge and the distance between the charge. Wait. So our charge and the distance between the charge. So when it's for the first one, Q3, the Q3 and the Q1, to now be 2 minus 2 times 10 raised to the power minus 6 divided by, what is the distance between them? The distance between them from here to this part is like saying 1 minus 0, and it will give us 1, plus for these two charges, it will now be 2 times 10 raised to the power minus 6 divided by the distance between these two from here to this part is like saying 1 minus 0.5 should give us 0.5 meter. So we'll now divide it by 0.5. So punching our calculator, we'll now have our answer. So if you solve this, you'll be having 0.027, which is approximately equal to, taking this one to this part, we'll be having 2.7 times 10 raised to the power minus 2 joules. So this is the work done to bring the charge from infinity to point X. Then for the part B, the electric potential energy of the system. When it comes to the electric potential energy of the system, we'll be considering each charges separately. When it relates with Q1, Q2, Q1, Q3, and when Q2 relates with Q3 also. So the formula we'll be using, our potential energy is equal to, this time, is equal to K Q let's call this one T, let's call this one J, all over. Remember, it is also energy, so our arrow will just be a single one. This time, our I is not equal to the J. Our I is always lesser than the J. That is, following alphabetical order from 1 to 2, 1 to 3. Our I must not be bigger than J, then 2 to 3. So now we're having our U to be equal to, since K is, our K is always constant, our K will be found outside, times bracket, the Q1 is minus 2 times 10 raised to the power minus 6 times 2 times 10 raised to the power minus 6 divided by, what is the distance? The distance from here to here is like saying 0.5 minus 0, which is equal to 0.5. Then for the other one, plus Q1, Q3, so now be minus 2 times 10 raised to the power minus 6 times 1.5 times 10 raised to the power minus 6 divided by, the distance from here to here is 1 minus 0, so it will give us 1, plus could just possibly write the other part here. So if I'm to write this part and this part here, to now give us Q2 and Q3 to now be 2 times 10 plus 2 times 10 raised to the power minus 6 times 1.5 times 10 raised to the power minus 6 divided by, from this point to this point, it's like saying 1 minus 0.5. 1 minus 0.5 is going to give us 0.5. So the distance between them here is 0.5. This one will give us the total potential energy that exists in the whole system, both for Q1, Q2, and Q3 separately, all of them. So the answer will now be, your answer will now be 4.5 times 10 raised to the power minus 2 minus 4.5 times 10 raised to the power minus 2 joules. The negative sign here is trying to tell us that the charge was brought from infinity, a Q3 was brought from infinity to point X, which is equal to 1 meter. So that is that for this question. So we're told to, from the question, we're told that they said, what is the electric potential at the center of the sphere? This center, the center of the sphere is this part. the distance from the center of the sphere to Q1 is r1, like that, r2, r3, r4. So we're told to find the electric potential. And normal, from our formula of electric potential, V is equal to KQ all over R. If we want to write it using our superposition law, it will not be summation. Since K is always constant, we write it at the back here. The number of charge we are dealing with there is about 4. Write it at the top. Then I equal 1. We are starting from 1. Now be Q of I all over arrow of J. Let's say arrow of I, because both of them are starting from 1 to any point they want to start to go to. So from there I can say our V is equal to K bracket Q1 all over R1 plus Q2 all over R2 plus Q3 all over R3 plus Q4 all over R4. This one telling us the point we are to end and where we are to start from 1, then we are to end at 4. Then from there, if you look at this diagram very well, you find out that the diagram is somewhat complex, but we can resolve it. If we take just this part, this place being the line, the diagonal of the square, this longest part being the diagonal of the square, we're told that this part is equal to 1, and this square is equal at all the sides, is equal at all sides. So if here is equal to 1 meter, definitely this part will also be equal to 1 meter. So in order to get the length of the diagonal, our arrow, let's call the length of the diagonal to be arrow, big arrow. Our big arrow will be equal to the square root of, or let's use L. L is equal to the square root of 1 square plus 1 square from Pythagoras theorem, and this will give us root 2. If you look at it very well, you find out that our arrow 1 is equal to, with the signs they place here, you know that these things, they are equal. Arrow 1 is equal to the arrow 2, and is equal to arrow 3, and is equal to the arrow 4, and is equal to, if we divide this diagonal into 2, or if you look at it, we're told that it was at the center of everything, you find out that you'll be having for the arrow 2 and the arrow 4, and we're told that all the results are equal. So we can say this is equal to the big arrow, that is the length of the stuff, over 2. The length of the stuff over 2 give us the parts for one arrow, that is 1 radius. So, and we're told that all the radius, they are equal. So from there I can say this is equal to root 2 all over 2. That is to say that for our value of arrow 1 is equal to root 2 over 2, value of arrow 2 is equal to root 2 over 2, like that in the end. So if we are to imply this to our equation we have dropped here, our K is equal to 9 times 10 raised to the power 9 bracket, our Q1 is 1 nano 10 raised to the power minus 9 divided by our arrow 1. Our arrow 1 is equal to the arrow 2 is equal to arrow 3 and equals to, and our arrow 1 is equal to root 3 over 2, root 2 over 2 rather, plus our arrow 2 minus 2 times 10 raised to the power minus 9 all over root 2 over 2 plus the arrow 3 is equal to 3 times 10 raised to the power 9, rather the Q3, 3 times 10 raised to the power minus 9 all over root 2 over 2 plus our Q4, which is equal to minus 4 times 10 raised to the power minus 9 all over root 2 over 2. If you punch this with your calculator, you find out that you arrive as plus 25.5 volts as your final answer. So this is the solving for this part. I'll be dropping another question. This is another question. I've solved about 2 questions which I've already posted already. And this is the third question. The third question, another electric potential. We're told that a charged oil of radius 0.3 times 10 raised to the minus is prevented from falling under gravity. As it was like suspended in the air, then by a vertical field between 2 horizontal plates. So let's have a pictorial view of what we are talking about. So assuming this the plate by 2 horizontal plates of potential 2 horizontal plates charged to a difference of potential of plate 7.3. So the potential difference that exists between the 2 plates, let's call it delta V, is equal to 7340 volts. We're told that the charge was suspended. We're told that the radius of the charge was 0.3 times 10 raised to the power minus 6. So for the charge to be suspended, the force of gravity and the electric field force that exists between the 2 charge plates must be equal. So we're told that the distance between the plates was, from here to here, the distance was 14 millimeter, and the density of the substance was 920. So we should calculate the magnitude of the charge. So first of all, for the charged oil drop to be suspended, it means that the electric field, the force exhibited by the electric field, must be equal to the force of gravity, and our force of gravity is equal to mg. The electric field is given from our electric field intensity, which is F all over Q. So therefore our F is equal to EQ. So EQ rather. So it will now be E times Q. This is what we are interested in. We're told to find the charge of the substance. But if you look at the question very well, we're not given the mass of the substance, but we're given the density. And we know that our density is equal to mass all over the volume of a substance. So from there, we can calculate our mass to be equal to the density times the volume of the substance. And since we are dealing with a oil, like a oil patch rather, the oil patch normal is assumed to take, and normal we said is assumed to take the structure of an atom, and we're told that atom at some point in time they experience their shape-like form is a sphere. So they are expected to take the volume of a sphere in this case, and the volume of a sphere is 4 all over 3 pi r cube. This is what we have as the volume of a sphere, and we're told that the density is 920. So if we are to get our value for Q here, the quantity of the charge, it will now be mg all over E, where our E is the electric field intensity. Then for the E, the electric field intensity, if you look at the question we're given, we're not giving electric field intensity, but we're giving the voltage and the difference between them. There's a formula that relates voltage and the difference between them. Remember that our electric field intensity is equal to, rather, our V, electric potential, is equal to W all over Q. Having that in mind, our W is equal to the force times the distance R over Q. And we know that force times distance always relates to the electric field intensity of a substance. So I can say V is equal to E arrow, and this arrow is the same thing as our D in this case. So this is the formula that relates the potential, the difference, and the electric field intensity. So from there I can say our E is equal to V all over D. So if I place our E here, anywhere I see our E to be V over D here, we'll find out that the D will go upward and our V will come down. We'll be having this value. If we look at the question very well, we're not given the mass of the substance. So in order to calculate for the mass of the substance, we know that our density is equal to mass all over volume, and our mass is equal to the density times the volume. So from there, our density was given, but we don't have the value for our volume. For this question we're given, we're told that the oil is going to take the shape of an atom, and normal for the oil here taking the shape of the atom, the shape it is carrying is the shape of a sphere. So we are going to be using the value, if we are going to be solving the value here, we'll be using the volume for a sphere, and the volume for a sphere is 4 over 3 pi r cube. So our density was given to be 920, 4 over 3 pi, our radius 0.3 times 10 raised to the power minus 6, all cube. So if we solve for that, our mass to be equal to 1.041 times 10 raised to the power minus 16 kg. So to get our value for Q now, our mass is 1.041 times 10 raised to the power minus 16 times our G, 9.8, times our distance between them, 0.014, divided by our V, which is the delta V, which is equal to 7.340. So if we solve for this value, we'll be having 1.946 times 10 raised to the power minus 21 coulomb as your answer. So that is that for this video. I'll be solving another question under this same video rather. For this question, we're told that an electric dipole of 2-point charge Q1 and Q2 placed 10 cm apart. Q1 and Q2 placed 10 cm apart. Placed 10 cm apart. We're told to compute the potential at point A, B, and C. The potential at point A, B, and point C. So first of all, we're told to compute the potential. The formula for calculating potential is KQ all over R, which is equal to summation K. For this time, we are dealing with 2-point charge. So we'll be starting for the first one. Q of I all over R of J, anyone will be using. So from there, since we are calculating the potential for A, B, and C, for point A, first of all, the V at point A, we will now say, let's consider the first charge, Q1. Our Q1 is equal to K bracket. Our Q1 is equal to 2 times 10 raised to the power minus 6 divided by the distance between Q1 from point A from here to here is 6 cm. which is also equal to, if you divide by 100, to give you 0.06 meter. Then the two charge, what we are trying to do here in this solving is to relate the potential that the two charge exert at point A. So since we have solved for the first one, for the Q1, the Q2 will exert plus, while the value for Q2 is minus 12 times 10 raised to the power minus 6 all over. The distance between that one from point A is 0.04. Remember, our K is equal to 9 times 10 raised to the power 9. So from there, if we are to punch our calculator, we'll be having minus 2.4 times 10 raised to the power 6 squared. No, since we are dealing with electric potential at V, its SI unit is in V. Its SI unit to be in V. So we can also say minus 2.4 microvolt. Then for point B, we are solving for point B. So now be V of B is equal to 9 times 10 raised to the power 9. For charge Q1 on point B, its distance is, Q1 first of all is 2 times 10 raised to the power 6 minus 6 divided by, the distance from Q1 to point B is 4, which is equal to 0.04 meter, plus the distance of Q2 to point B is 6 plus 4 plus 6, which is equal to 14. If you divide that by 100, it will give you 0.14. And our value for Q2 is minus 12. Minus 12 times 10 raised to the power minus 6. So if you punch your calculator, find out that our value will give us minus 3.21 times 10 raised to the power 5 volts. This is also equal to, we can say 0.321 times 10 raised to the power 6 volts, which is equal to minus 0.321. Oh, rather, this is not micro times 10 raised to the power 6. Then 10 times 10 raised to the power 6 volts. This is not micro scale. I wish it was minus 6. We would have said it's a micro scale. But since it's just 10 raised to the power 6, we can call it a milliscale, rather, a millivolt, if that is necessary, but it's not necessary yet. Then for point C, let me clean this part and solve it here. Our V is equal to K bracket Q1 all over R1 plus Q2 all over R2. So from there, our K is 9 times 10 raised to the power 9, always constant. Our Q1 here, the distance from Q1 to point C is 13 centimeter. And if you look at the triangle that is placed here, you find out that it's an isosceles triangle. Two parts are equal to each other. So here is also equal to 13 centimeter, but this part is different. So I can say from there that the distance between Q1 to Q1 to point C is 13 centimeter. Then our value for Q1 normal is plus 2 okay, let's just solve. Plus 2 times 10 raised to the power minus 6 divided by, our R1 is 0.13 meter. Then for the other one, plus bracket minus 12 times 10 raised to the power minus 6 divided by 0.13 meter. So if we solve this part, we'll be having, at the end, we'll get minus 6.92 times 10 raised to power as our answer. So that is the calculation aspect for electropotential. In our next class, I will be teaching you guys capacitor.